La la la. Here we go. So as you know, I try to begin every video with a word of prayer. So let me pray again as to annoy the internet. Nah. Sorry. Certain elements of the internet. Thank you. I will begin. Dear Father, just guide our thoughts on polar coordinates this morning, Lord. In your name I pray. Amen. Okay, so polar coordinates. So hopefully most of you have seen something about this before. Basically, here's the deal. If you pick a point in the plane, right, let's say x comma y, right, then you can describe that point either in Cartesian coordinates, as I just did, or in polar coordinates, right? So the distance from the origin out to there is called the radius, r, and the standard angle in counterclockwise fashion, that's the positive, quote-unquote, positively oriented, wow, nice, positively oriented angle is the standard angle, right? All right, so what are the relation between these? Well, x is equal to r cosine theta, y is equal to r sine theta, all right? And this annoys me, but in this part of the course, it's traditional to let r equal to plus or minus the square root of x squared plus y squared, depending on the context. Now, I really prefer to just say r is positive square root, but I have to admit, for the purposes of polar graphing, often we allow r to be negative. So let me just say that. Next semester, if you have me, only plus. So let me just show you what I'm talking about for a second here. In terms of r being, if I look at something like r equals to the sine of 2 theta, right? Well, if we graph that, here's 2 pi. I'm looking at the r theta plane here for a second, okay? So what does sine of 2 theta look like? It's just the sine function, double speed, so to speak, right? So if you go from 0 to 2 pi, you've got how many cycles of sine 2 theta? You have 2 cycles, right? So this is what sine 2 theta looks like if we go all the way from 0 to 2 pi, right? And so what's that point? You got pi over 2 here, you got 3 pi over 2 here. And so, you know, if we only allowed, so let's see here, here's x, here's y. Where is pi over 2? Where's 3 pi over 2? I'll draw a graph over here. This is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4, right? In quadrant 1, we've got theta equals to 0 here. Up here, you've got theta equals to pi over 2. This one's theta equals to pi, right? Down here, we've got theta equals to 3 pi over 2. In case you forgot, that's how the angles work, you know. So if I look at the first, you know, going from 0 to pi over 2, that's going to give me something like this, right? And so I'll try to use some color coding here. That's that part. And then going from pi to 3 pi over 2, so that would be from pi to 3 pi over 2. I've got something like this, right? And that would be it. If we only allowed r to be positive in polar graphing, that would be all we got. But the tradition is to allow r to be negative. So if r is negative, how does it work, though? So between pi over 2 and pi, so that's between here and here. Between pi over 2 and pi, I have r less than 0. And so the way that's understood is you flip it 180 degrees over, or pi over. So that gives us this one. And on the other hand, between 3 pi over 2 and 2 pi, all right, well, 3 pi over 2 and 2 pi would be here, but the thing is r is less than 0, so that flips it across the origin over to here, and it gives you this lobe. And this is how software, like Desmos and other things, are set up to graph typically. So if I was you know, for mathematical reasons, I like to just let plus square root be all I'm looking at. All right? Do you understand why that is? It annoys me that in the other way of thinking, if I told you that the point, you know, if you had point 1, 1 has, I'd like to say r is equal to the square root of 2 and be done with it. And that is what we'll say in here, except when we're graphing. All right? See, because, well, here's how we'll clarify it. R is equal to the square root of 2 with theta equals to what? What's the angle for 1, 1, the point 1, 1? What's the standard angle for that? What's that? Pi over 4, right? How did you guys figure that out? You're like, that's such an easy angle. I don't need to, I can just see it, right? Fine. So I heard pi over 4. But you could also say it's got minus the square root of 2 with theta equals to what? The answer is pi plus pi over 4. So I don't like this. Personally, this bothers me. From just it's just tacky to me in some sense. Because my polar coordinates are not, you know, I have these two different sets of polar coordinates which describe this same point. That means that they're not, technically speaking, coordinates. But it's convenient for graphing. All right. So we're looking at r equals what? There it is. So as you can see, it's not just me that allows r to be negative. It's typical software, yeah, and typical calculus books in this part of the course. But later, when we talk about polar coordinates in Calculus 3, we insist on r being non-negative. We insist on it being the positive square root. So just that's a distinction, and yeah.
I don't understand what that is.
What is that? Yeah.
How's it being graphed?
That's looking at the graph r equals to sine 2 theta. It's a set of points in the plane for which r is equal to sine 2 theta. What is that? What is that? Well, so you're starting to wonder, what is it in terms of things I already know, right? Perhaps. So in terms of things you already know, we could take this and we can multiply that by r again, or maybe r cubed. I'll multiply both sides by r squared. Excuse me. So I get r cubed is, and I'll multiply by 2. So 2 r squared times 2 sine 2 theta. Oh, I'm an idiot. I don't need the 2. You guys tell me. What is sine 2 theta equal to? Can you tell me what sine 2 theta is? It's what? 2 r cosine theta, r sine theta, am I right? Right, because sine 2 theta is 2 sine theta cosine theta. So apparently this is x squared plus y squared to the 3/2 power equal to 2xy. Now, I don't remember if Desmos is okay for, I'm not sure if Desmos can hack that. What did I just have? X squared plus y squared. Oops. What was it, 2xy? Oh, there you go. I guess it can. So there you go. The blue is the Cartesian solution to that. Because what did I not include? Plus or minus. See, I assumed r was equal to the square root of x squared plus y squared in what I did in the brown right here, so I only got half of that, because the other half corresponds to r being negative. To throw in the minus, I can either add another graph and just chuck a minus in there, I think. I think that we just put a minus here. Yeah, look at that. Here, I'll make it a different color. Maybe make it red. Orange, have orange. There we go. Turn this off here for a second. So as you can see, the ones for the plus, ones for the minus, correspondingly, r is either positive or negative. But, so you're like, oh yeah, I remember when I studied solution sets to Cartesian equations. I remember when we talked about how if you look at the 3/2 power of x squared plus y squared equal to 2xy, that's a four-leafed rose. Or four-leaf, it's a flower with 4 petals. I hope says none of you, because that's not something you did, right? I mean, did you? I didn't. The first time I ever saw such pictures is when I studied graphs of polar functions. So generically speaking, if we look at r equals to some function of theta, that's called a polar graph. And it gives us all kinds of neat new shapes that we perhaps haven't seen before. Yep.
I was just curious how you went from the what's it called, the sine, where it's just the wave, to the actual like clover that we got. Are you rearranging variables?
Let's do another one. What I'm doing is I'm using the geometric definition of r and theta, all right, to guide my plotting in the xy plane. I'm using the information in the r theta graph to create the xy graph with the guide of the definition of the polar coordinate system, which includes both the plus and the minus r, unfortunately. Let me show you another example of this. We'll make it really simple in terms of the polar graph. Let's graph r equals to theta. So what does r equal to theta look like in the r theta plane? It's just this, right? So we could, take some benchmarks here, pi, 2 pi, and so forth. Let me make this 2 pi. Go maybe a little bit greedier here. Pi, 2 pi, 3 pi, 4 pi, etc., right? So pi is about 3. That's about, well, anyway. So that's my r theta graph. It's rather boring. R equals to theta. What's the corresponding Cartesian graph look like? X equals to r cosine theta. Y equals to r sine theta, right? So the Cartesian graph we could look at as x equals to theta cosine theta and y equals to theta sine theta. In other words, we could look at it as parametrically the path t cosine t, t sine t. I mean, you could look at it as a parametrized path where the parameter is theta. That's one way you could understand it, all right? But you asked me, how do I create the picture? So let me try to explain that. So, all right. So I start out at 0, right? By the time I get to pi over 2, I'm at pi over 2, right? So let's suppose that that's like here. So I go from 0, I go over here to pi over 2. When I get to pi, I'm at twice that. When I get to 3 pi, I'm a little bit further out. When I get back to 2 pi, I'm double that distance. When I get to, when I get to 4 pi, I'm like here, right? So it's got to be something like, and it just keeps going. But basically, I'm just following, let's see here. It's like x and y, yeah. I mean, you might ask me, what's the Cartesian equation of the spiral? I don't know right offhand. I could try to find it. To find the Cartesian equation of the spiral, we'd have to take, x equals to theta cosine theta, and y equals to theta sine theta. Take these and eliminate theta. Can you do it? You might be able to do it, but I think it's more fun with the remaining class time that I don't have to add a slider, b, and see what happens when we see if you don't have a whole number. If you don't have a whole number, you'll keep going and going. If I was to expand this to 100, see. So, but if I pick a whole number, we'll get. If it's an odd number, we get 7 petals. What happens if we have an even number? Think we'll get 6 petals? We get 12. So for 5, we'll get 5 petals. But for 4, we'll get 8. And you can play the same game with cosine.
Is the 5 one actually 10
Maybe that's a way of looking at it. Yeah. Yeah, that's probably the case if we go from 0 to 2 pi. Yeah. Thanks, guys. Have a good weekend. You already hit it?